In this video, we're going to discuss the periodic trends in atomic radius. And basically what this means is what happens to the sizes of atoms as you move across a period or as you go down a group. And what happens to the atomic radius is based on this idea of effective nuclear charge. And you might remember that we came up with an estimate, an equation whereby we could estimate the effective nuclear charge on a particular atom. That is, we just take the full nuclear charge that you get from the atomic number, like 4 for beryllium, and from that you subtract the number of core electrons. And what effective nuclear charge refers to is the ability of core electrons to sort of shield the valence electrons from the nucleus itself. Now, as you move across a period, as we move, say, from sodium to argon, what you'll find, and you should do these calculations, is that you'll find that the effective nuclear charge, according to this estimate, for sodium is 1, for magnesium is 2, for aluminum is 3, for silicon is 4, for phosphorus is 5, for sulfur it's 6, for chlorine it's 7, and the estimated effective nuclear charge for argon is 8. And we see that as we move across this period, or really any period, that the effective nuclear charge that we estimate goes up as you move across a period. And that has the effect of causing the size of the atom, the atomic radius, to shrink. I mean, if you can imagine, we'll just do this simple case of comparing lithium to neon. In lithium, there's a +3 nucleus that has a valence electron, a single valence electron, and then there's 2 core electrons. And from Z star estimate, we see that if we take the atomic number of lithium, which is 3, that's the same as Z, and we subtract the number of core electrons, we get 1. And that means that this electron, this valence electron, sort of feels like it's attracted to a nuclear charge of only +1. Now, if we compare that to neon, in the case of neon, the nuclear charge is 10, and then there's 2 core electrons, and outside of that, there are going to be 8 valence electrons. And I'm just showing this in a Bohr model because it's useful in this particular case and simpler to use the Bohr model. So if I'm going to estimate Z star, that's right, the effective nuclear charge, if I'm going to take the estimated effective nuclear charge for neon, we're going to take 10, subtract the 2 core electrons, and get 8. And that means all of these valence electrons experience a sort of like a +8 pull by the nucleus. That's a much stronger attraction of these valence electrons for the nucleus in neon than is the case for lithium. And as a result, the valence electrons are contracted a lot more due to this greater attraction. And so we'd expect a smaller atomic radius for neon and a much larger one for lithium. Indeed, if we look up the atomic radii for lithium and for neon, we find that the atomic radius of lithium is 1.28 picometers, whereas the atomic radius for neon is 0.55 picometers. And we see this trend go all the way across any period. You tend to see the atomic radius drop as you go across a period. That's the general periodic trend that one sees in atomic radius. Go across the period, and the atomic radius drops. There are fluctuations occur, but we just want you to know the overall pattern. Now we're going to ask the question, what happens to atomic radius as you go down a group? And this question is actually quite easy to answer if we recognize that in any particular group, the effective nuclear charge that we estimate is going to be the same. So for the alkali metals, Z star estimate ends up being 1, Z star estimate ends up being 2 for the alkaline earth metals. And so what ends up happening is as you go down a group, you should recognize that you're adding shells. So if I take, for example, lithium, we have the first electronic shell if I'm using the Bohr model. And then we're going to have to put that valence electron in the second shell. And in this case, you'll notice that as we move from lithium to sodium, we actually have to add a third shell. And the addition of that third shell moves that valence electron further away from the nucleus than in the case of lithium. So this would be lithium atom and this would be a sodium atom. And so because you have both electrons basically being attracted to the nucleus with the same effective nuclear charge, that's not going to have an effect on the shrinking of the atomic radius because those are equal, right? I mean, they're both having a positive 1 attraction. But we notice that a sodium atom is going to have a larger radius because, well, we're adding shells. And every time you add shells, that electron, those valence electrons get further and further and further away from the nucleus. So, for example, in the case of francium, we have to go all the way to the 1, 2, 3, 4, 5, 6, 7th shell. Once again, with francium, we're going to have Z star estimate as 1, but we got to do 7 shells. So that's 1, 2, 3, 4, 5, 6, 7. We've got that valence electron way out here. And so you see as you go down a group, because of the addition of shells and the fact that Z star pretty much stays the same going down a group, that as you go down a group, the atomic radius increases. And that holds for almost all the, for all the families in the periodic table. Again, with fluctuations, but as you go down a family, the atomic radius increases because of the addition of additional shells.